Today we look at simple harmonic motion. Certain oscillating devices move with a type of motion called simple harmonic motion. Okay, an example of such a device is a mass hanging on a spring which is given some displacement and then released. So if we had a spring securely attached to some sort of support structure, and beneath the spring there was a mass, and we pulled that mass down slightly and released it, the mass would rise and fall, rise and fall. That oscillating motion would be simple harmonic in nature. So each time that mass moved away from its midpoint, there would be a restoring force. The spring would try and pull the mass back to the midpoint. Now that restoring force would be directly proportional to the displacement. Now the displacement would be how far we are from the midpoint. And furthermore, that restoring force would act in the opposite direction to the displacement. The type of spring we're talking about in this example would be a close-coiled helical spring, much like these two examples here. And basically, when displaced either in tension or in compression, it would have a restoring tendency back to the original position. Right, now this type of motion is quite complex in nature. It's not a linear matter of a linear change in acceleration or velocity, but it is best visualized by considering an imaginary arm rotating at a steady angular speed in this imaginary circle. So lots of imaginary things going on here, but let's picture a circle, and let's picture an arm on that circle pivoting about point O, and let's have this arm rotate at a steady angular speed of omega around and around. Then let's focus on the end of that arm, and let's project a point straight downwards to this diameter line, and let's focus on that spot where the red dot is now. As the arm rotates anti-clockwise, this projected point would shift, and by the time the arm was vertical, it would be here, and by the time the arm had moved all the way to the left, the point would be there, and then it would start moving backwards again. And the progress of this red dot backwards and forwards would be simple harmonic in nature. Now, before we dive into the workings of this motion, let's consider logically the rate of movement of this red dot. When it moved outwards to here, it would momentarily stop at that point. So the velocity would become zero. And then it would start back again, and it would be going at its fastest by the time it got here. So it would be moving from right to left as quickly as it ever goes. In other words, the highest velocity would be here. Then it would start slowing and slowing and slowing, and ultimately it would stop momentarily there and start to go back again, faster, faster, faster. It would reach its fastest speed here, and it would start slowing, 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 stop momentarily, and go back again. So that red dot would be moving with simple harmonic motion. And just looking at it logically, highest velocity would be at the midpoint, and here where it stopped momentarily, the acceleration, strangely enough, would be at the highest. And here again, it would be at the same numeric value. Here, where it was going at its fastest velocity, acceleration would in fact be zero momentarily at that point. Now, what's vital to remember here is we don't really have a circle, and we don't really have an arm rotating. We are just using this to visualize the motion of this projected point backwards and forwards. And that motion is the motion that would be possessed by this mass as it rose and fell. So at its midpoint, wherever that is, it would be going at its highest velocity, and the acceleration would be zero. And when it reached its highest point, the velocity would now be zero, acceleration would be highest, and again that would occur at the lowest point. Now, as with any oscillating motion, we can talk of periodic time and frequency. Remember, periodic time is the time taken for one full oscillation. So for the mass to go from its highest point to its lowest point and back again to the highest point would be the periodic time. However many seconds that took would be t. And frequency is the inverse of that, remember. That is measured in hertz, and it is the number of cycles per second, or oscillations per second. So those are important to remember. But now remember, whilst one periodic time occurred, this arm rotated one full circle. So we can relate periodic time to the speed of rotation of this imaginary arm. Remember that it is an imaginary arm. There isn't really an arm rotating. Now let's talk about displacement. O is the midpoint, and P, remember, is that projected point on the diameter. So if we take this line and we redraw it down here beneath, here is our midpoint, and at this particular instant where the arm is where it is, point P is here, and X is the displacement. Displacement is simply the distance traveled from the midpoint outwards, and when it was, let's say, over here, the displacement would be that much. Now OB and OA, they are obviously the same. That's actually the radius of the circle, and that is also known as the amplitude of the motion. Remember what amplitude is? That is the maximum extent of a vibration or oscillation measured from the position of equilibrium. So let's start with a few important formulae. Displacement is probably the easiest one to figure out, because basically cos theta is x over r if you consider that small triangle. So we can relate x, the displacement, to r cos theta, theta being the angle from the horizontal to where the imaginary line is at any one instant. The velocity of point P at any instant is found with omega r sine theta, and the acceleration is omega squared r cos theta. The units, of course, would be meters for displacement, meters per second for velocity, and meters per second squared for acceleration. And before we move off this page, as we discussed earlier, acceleration is maximum at A and B and 0 at O. So acceleration was highest over here and over here, or over here and over here if you prefer, and acceleration is 0 at the midpoint. Conversely, the velocity is a maximum when you pass point O, and it is 0 at the two ends. To better visualize all of this, I'd strongly suggest you go and have a look at this link over here, which shows you a little simulation of the motion. So let's kick off with an example. This example says a particle oscillates with simple harmonic motion and has amplitude 75 millimeters. Remember what amplitude was? That was the distance from here to here, the maximum extent of a vibration or oscillation. So the furthest it got from the midpoint was here or here. So amplitude, remember, is radius. So we already know the radius of our imaginary circle, which I've drawn over here. Periodic time was half a second. What that meant was to go from any point back to that same point would take half a second. We must find the maximum velocity and the maximum acceleration. So one full turn of our imaginary arm, who's rotating at omega, will take half a second. So to go from any point, let's make it this point, all the way around back to that point will take half a second. So if we rotate one full circle, which is 2 pi radians in half a second, our rate of rotation would be 12.566 radians per second. Right, they asked for maximum velocity. Now we know that maximum velocity occurs at the midpoint, and when you're at the midpoint, displacement is 0, and theta would be 90 degrees because this arm would be straight up and the angle would be 90 degrees. So we use our formula for velocity. Velocity is omega r sine theta. So omega is 12.566. R we know is the same as amplitude, and when the arm is vertical, theta is 90 degrees. So it works out to 0.943 meters per second. Straight away, let's do maximum acceleration. It occurs when displacement is equal to r, in other words, at the end here or the end here, and theta at those 2 points would either be 0 degrees or 180 degrees. So the acceleration formula says omega squared r cos theta. Omega is 12.566, it gets squared, times r, which is amplitude at 0.075, times cos, let's use 0, and you find 11.9 meters per second squared. Here's another one. It says a point moves with SHM and has a velocity of 1.4 meters per second when it goes through the midpoint of the motion. Now remember, that's significant because at the midpoint it would be traveling at its fastest, so that is maximum velocity, 1.4. Note that down. The period of oscillation is pi seconds, so that's 3.14159 seconds is how long it takes for one oscillation. Calculate the amplitude of the motion and the velocity at a point 330 millimeters from the midpoint. So periodic time is pi seconds, and we know that periodic time is related to one rotation of our imaginary arm, which would be 2 pi radians. And from that we can find that omega, which is the speed of rotation of the imaginary arm, is 2 pi radians per second. Now, they said that at the midpoint we were doing 1.4 meters per second, and that is the max velocity position. So use your your velocity formula. V is omega r sine theta, and remember that at the mid position theta would be 90 because the imaginary arm is straight up, and we can then go and find that r must be 0.7 meters, and r, which is the radius of the imaginary circle, is also equal to the amplitude, remember. Now the final thing we've got to find is the velocity when we are at 330 millimeter displacement. So if you draw out the circle, we could include the circle if we wanted to, but here's just the arm drawn. And when we are at 330 millimeters, it would mean that our projected point is 330 from the midpoint, like I've drawn here. And 0.7 meters, of course, is our amplitude, which is the radius of the imaginary circle. So in fact, let's just draw the imaginary circle in position here just to make it easier to understand. So there's our circle. And at this position here, we can in fact find theta, because cos of theta would be 0.33 over 0.7. So theta at this instant would be 61.873 degrees. So using our velocity formula, omega is known, came from there. R is known because that is amplitude. And sine of the angle that we're at now, sine 61.873, would suggest that at this instant, our projected point, the one moving backwards and forwards with SHM, is traveling at 1.235 meters per second at this instant. Now if we go back to the beginning and look at where we started, this mass, once displaced, would oscillate backwards and forwards. That is reasonably okay to understand. But now, how would the mass relate to the period of oscillation, and how would the spring stiffness feature in all of this? Obviously, both are going to have an effect on the rate of oscillation. Let's start by refreshing our memories on what spring stiffness is. So here is a spring, and let's apply a tensile load to the spring. Now, when that tensile load is 0, the spring would be at its original length, undeflected. And as we applied a load P, we would find that the spring became longer. Now, let's say it becomes longer by X. The spring stiffness would be whatever load you applied, P, over whatever deflection you achieved. Now, the units of that would therefore be newtons per meter. Okay, so spring stiffness is measured in newtons per meter. And whatever that number is, it stays with the spring. You could just as well write it on the spring if you could, because regardless of what amount of force we're dealing with, that stiffness would live with the spring and relates to the properties of the spring, the wire diameter, the coil diameter, the material, etc. Let's place a mass on a frictionless surface and attach it to a spring. Deflect the mass and release it. That mass would oscillate backwards and forwards with SHM. And here is the relationship we were leading up to. The periodic time of oscillation would be 2 pi and square root m, mass in kilograms, over spring stiffness. Remember, the units of that were newtons per meter, what we just discussed moments ago. So that is an important formula to note down on your summary sheet. So as usual, let's get going with an example. A 4 kilogram mass attached to a spring is observed to oscillate with a period of 2 seconds. What is the period of oscillation if a 6 kilogram mass is attached to the spring? It's the same spring. Okay, so let's forget that part first and just start with the first bit. Periodic time is 2 pi square root m over k. Periodic time, we were told, was 2 seconds initially, equals to 2 pi square root 4 kilograms is the mass we had initially over k. So we can solve for k and deduce that the stiffness of this particular spring is 39.47 newtons per meter. Now remember, that very same spring now had the 4 kilogram mass removed and a 6 kilogram mass put on it instead. So what changes? Well, the spring stiffness does not change, but the mass changed. So the periodic time will now be different. It will now be 2.45 seconds. Does it make sense? It used to be 2 and now it's 2.45. Well, I think that makes sense because we're dealing with a bigger mass. The mass is now 50% greater at 6 kilograms. And the periodic time of oscillation has increased from 2 seconds to 2.45 seconds. Now we start dealing with time. Time to go from a point to another point in our motion. And that is very easily explained by relating matters back to this imaginary rotating arm. Because remember, it turns at constant angular velocity. Unlike our projected point, which definitely does not move with constant velocity or constant acceleration. Both are changing all the time. So you can imagine the calculation is much more complex if you consider this motion versus the steady rotation of this imaginary arm. So that's the good news. Working out time is going to be much easier if we relate it back to that rotating arm. So in our first one here, relating to time, a block of mass of 2 kilograms is attached to a spring with a constant 18 newtons per meter stiffness. It is moved to a point where the displacement is 2 meters and then released. So obviously it then oscillates backwards and forwards. How much time does it take for the block to travel to the point where the displacement is 1 meter, wherever that point is? So let's start by working out the periodic time of oscillation, which we know relates to spring stiffness and mass. So 2 pi square root m over k tells us that the periodic time of oscillation is 2.094 seconds. How fast is our imaginary circle, or imaginary arm rotating rather? T is 2 pi over omega, one full rotation, divided by omega will give us how long it took. So we find omega at 3 radians per second. That is the speed of rotation of the imaginary arm. Now remember that the mass was displaced to a point where it was 2 meters from the midpoint. So that must be our maximum displacement, which also must then be our radius of our imaginary circle. So it is the distance from here to the outermost point at 2 meters. And we are told to work out things when the displacement is at 1 meter, which is exactly halfway between those 2 points over here. And if we look at our velocity formula, at our displacement formula rather, displacement of 1 meter is equal to radius, remember that's now 2, cos theta. What must be the angle when we have a displacement of 1 meter? Well, we solve for theta and we find that it is when the arm is at 60 degrees to the horizontal. And 60 degrees in radians, remember to convert degrees to radians, multiplied by pi over 180, ends up at 1.047 radians. Now to answer the question, the time to move from x equals 2 meters to x equals 1 meter. So how long does it take for our projected point to go from here to here? Well, during that time, our imaginary arm traveled 60 degrees at a rate of 3 radians per second. So how long would it take? Well, omega, speed of angular rotation, is theta over t, radians over seconds. So we can solve for t. T is, therefore, theta over omega. Make sure you put in theta in radians, 1.047, divided by the rate of 3 radians per second, means it will take 0.35 seconds to travel from here to here. Here are some additional examples for you to try. Start with this one over here. And move on to this one. And then try that one, that one, that one, and finish off with that one.